Thank you to everyone for joining us today at the Blast AI Research Symposium. Today, we'll be presenting the culmination of the past 8 weeks of our research. Deep learning approaches for optimized web accessibility, correcting violations and enhancing user experience. In this presentation, we will begin by describing the background of our problem, as well as our big picture approach to tackling web accessibility failures. Then, we will discuss our approach to solving these problems, including data collection, prompt generation, and error correction. We will then discuss the results of our research, including benchmarks for measuring success and an example webpage before and after corrections. Finally, we will conclude with implications for our work and possibilities for improvement and for future work.
But first, let's get into the problem that is web accessibility. 16% of people worldwide experience significant disability. And with such a large population affected and the rapidly increasing quotidian use of software, web accessibility is a major issue. 75% of Americans with disabilities use the internet daily, yet most websites are not designed with accessibility in mind. This prevents people with disabilities from fully participating online. 90% of websites are inaccessible to people who rely on assistive technology like screen readers. This technology helps people with disabilities use the web, but inaccessible design prevents them from accessing information, making their usage completely redundant. 67% of people rate web accessibility plugins, widgets, or overlays as not very effective. These band-aid solutions don't address inaccessible underlying code. The figures above demonstrate both the overall annual legal impact of web accessibility errors and common web accessibility failures. As seen in the figure to the left, lawsuits have been enormously increasing, with an increase in 2,011 lawsuits from 2017 to 2021. Despite these being explained by the causal increase in software use and development, it does not excuse the overwhelming discrimination caused by accessibility errors. As seen in the figure to the right, the 6 main web accessibility errors include low contrast, missing alternative text, empty links, missing form labels, empty buttons, and missing document language. These errors do so much, but the specifics are they make content difficult to read, especially for those with low vision. They prevent screen readers from conveying visual information to blind users, and they do not allow for keyboard usage, preventing use by those with motor disabilities. The conventional approaches for web accessibility are usually involving manual auditing of code to identify violations, and then human editors correcting the errors to make the content accessible. This process requires extensive time and resources. It is inefficient, difficult, and very error-prone. A better solution is needed to automatically detect and correct violations to create accessible web content.
So let's take a look at the big picture. The goal of our project is to use Playwright API to find web accessibility violations in the domain of our website. Then we used a large language model, which is a computer system that understands and generates human-like text. And one example of an LLM, and the LLM we used in this example was GBT. We then used prompt engineering techniques to optimize accuracy. Prompt engineering is when a user modifies their form of question or prompt to a language model in an attempt to get an answer that best fits their needs. In this case, we wanted a website design that was the most accessible. After passing it through the large language model, we wanted to get the corrected version of the domain to get more accessible website content for users. So let's take a look at the existing work on this topic. Past research has suggested the possible efficacy of using AI to automatically or at least semi-automatically fix errors. For example, a study from 2022 suggested the possibility of using NLP to approach handling HTML documents compared to other baseline models. The paper also highlighted the benefits of using AI, including saving resources, time, and improving accuracy. Another paper from 2020 specifically targeted one web accessibility error, the lack of alt text for certain images, and saw that an automatic computer vision algorithm could be used to automatically generate alt text. However, it also brought up the flaws of automatic strategies as it can lack accuracy sometimes. This was further shown through a 2019 study that was only able to increase web accessibility by 2.49% with an automatic correction system. Ultimately, we want to create a model that reaps the resource-efficient benefits of automatic corrections while maintaining the accuracy that comes with semi-automatic corrections that have more human control. In order to accomplish this, we aim to 1, create a data set including multiple URLs. 2, identify web accessibility violations using Playwright API, which basically is a program that returns the web accessibility violations given a URL. And 3, to use prompt engineering and LLMs or large language models to fix violation errors. So looking at our approach, we first ran web URLs through Playwright API, which returned the web accessibility violations of a given website, including the HTML of the errors, as well as the descriptions and suggested changes. We then used various LLM models alongside prompt engineering to automatically generate corrections. And once we implemented the corrections in the domain or the DOM, we ran the modified DOMs through the Playwright test once again to compare the severity of the original errors prior to fixing it with the severity of the errors after the corrections and after we ran it through the LLM.
Okay, so here is our formal pipeline to achieve our results. So first, as mentioned before, we had to create our data set of violations through the Playwright API. Afterwards, we designed several prompts or queries using a system and user message. We then fed these into OpenAI's language model, GPT, to create a suggested change. And finally, after iterating through the entire data set, we implemented the corrections by updating the DOM. So this is what our data set looks like. On the side, you can see we've included various features to describe the data, but mainly use the impact column, which details how severe a given violation was. For instance, the impact score for a violation could be critical, minor, cosmetic, moderate, etc. We ended up summing this column to see how severe the data set's violations were in total, and later on, we used it to evaluate the effectiveness of our approach. Additionally, we use the HTML column to see incorrect tags, the DOM column to see the entire website's HTML, and later created a DOM corrected column for implementing corrections. Following our dataset creation, we needed to feed in our requests to the model, but different requests can yield different results, some of which may be better than others. This process is known as prompt engineering, which is the practice of refining input prompts to obtain desired outputs or improve the performance of an LLM, in our case, GPT. As a system message, we fed in the URL, the error, a description, the suggested change, and finally, the incorrect line of HTML. As a user message, we use several different prompting techniques, which include few-shot prompting, which involves giving multiple examples to the model. React, as shown on the screen, is a process where you give a reason and an action to the model, and tree of thought, where it is a process where you ask the model to critique its own processes.
We use the find and replace method to correct the DOM of each URL in the dataset. Incorrect HTML tags were extracted from the dataset, and corrected HTML tags were extracted from GPT's response using regex. The corrected HTML tags were iteratively inserted into the DOM through the use of an error fix dictionary, until each URL was left with one final corrected DOM addressing all the errors from that URL. To measure the success of our DOM corrections, we implemented an impact score system which summed numerical representations of the impact of all the errors from a given URL. Our dataset included the initial impact scores of each URL, and after modifying the DOM, we applied the same scoring system to the remaining errors to evaluate the success of our models. The results of our research are shown here. Using React prompting with the GPT 3.5 model, our corrected DOM achieved a 38% decrease in impact score of website violations. The GPT-4 model had a 4.891% better performance than the GPT 3.5 model. Overall, the average number of violations per URL decreased by 41.463%. The best performance was achieved using React prompting with the GPT-4 model. Further prompt engineering techniques could be utilized to improve these results.
So what does a website like this look like? So here is an example web page before and after we ran our DOM correction approach. So some key differences that you can see is that our HTML corrections implemented were a highlighted search button and easier to read text due to more contrast, larger size, or bold text. These corrections enable web content to be more inclusive and accessible to a broader spectrum of users.
To sum it up, our project identifies accessibility violations from numerous websites using both the Playwright API and OpenAI's GPT-5 Turbo and GPT-4 models. By prompting OpenAI to correct our DOM, we're able to see a significant decrease in the severity score from the number of accessibility violations. Using this novel approach to correcting our accessibility violations will prove to be useful in the future, as this method is effective and keeps resource usage to a minimum.
So what are the future implications of our research? In the real world, such automated violation correction methods could easily be adapted into a graphic, web-based tool to enable website designers to easily test their accessibility or the website for accessibility and efficiently implement necessary corrections to establish fully accessible websites. Our research takes strides towards digital inclusivity for all by tackling the widespread prevalence of inaccessible websites. Our work also enables impaired individuals, such as colorblind or other visual impairments, to receive critical online information easily, such as applications like banking, shopping, healthcare, or signing online important forms. Greater web accessibility also allows for increased customer satisfaction and user engagement on business websites. This will lead to further increase of website use and creating a positive feedback loop that ultimately results in more business revenue. Accessible websites also allow businesses to spend less money on maintenance and website issues, reducing expenses. As we saw in 2021 alone, there were nearly 3,000 lawsuits due to website accessibility issues. By automating website accessibility corrections, fewer lawsuits due to lack of web accessibility will arise, meaning less time and money is spent on legal actions, and efforts can instead be prioritized for the online application quality. So the future work, what future work can be done based on the research that we've done? So ideally, you would want the severity score to reach 0, which symbolizes the comprehensive correction of accessibility violations. And future work can target this goal by, first of all, expanding the dataset size and diversity to empower our models to effectively address an even broader spectrum of accessibility challenges, such as tackling websites in different industries and different sectors. Improving corrections through other models such as Llamas, Vicuna, Cloud, Orca, and other models, or improving the prompt engineering techniques. And third, tackling specific errors through hybrid models. For example, we could integrate computer vision with natural language processing to specifically target missing alt text errors. These are the references for some of the pictures you guys saw throughout. And we would also like to thank BLAST for providing us with the support and resources to conduct this research. And we would also like to acknowledge Playwright API for giving us the accessibility violations and GPT for being the LLM that we used to make the corrections. Thank you guys for listening. Any questions?
Awesome presentation. I have one quick question. So you spoke a little bit about, applying this in scale to a bunch of websites. How will this look like if you were to apply it to a bunch of, say, commercial websites? Do you think the accuracy is there yet? And if not, what steps can be made to improve it?
I think that's a great question. I believe that future work needs to be done to further improve the accuracy, whether that means using more advanced LLM models with more parameters. However, I believe that using the current framework that we've developed in the past few weeks, there can definitely be more strides in saving resources, saving money, and labor for a lot of companies that may not have the resources to fix it with humans. So using LLM models can be a great tool to automatically fix these violations. And as we saw in our results, we were able to improve web accessibility violations by around 65%. So although there are a lot of strides that need to be made, it's a huge win that we were able to address at least half of or a majority of the web accessibility violations.
Yeah, that's awesome. And I'm sure that translates to hours upon hours saved. Stephen asked, how large is your data set?
So our data set is currently around 18 URLs. We had to drop certain ones due to errors with Playwright, but we have future plans to expand this data set to at least around 100 URLs.